Yeah, they have already gone on mute.
Yes. Sir, I will also switch off my video, sir, for better bandwidth.
Okay. Okay. So good evening to all of you. Welcome to this live interaction session for the course Operations Research, Introduction to Operations Research. I am the course instructor, Professor G. Srinivasan. We have the three TAs for the course who have been working with you, Swaminathan, Vasant Raj, and Jnanadeepa. All three of them are research students in the Department of Management Studies at IIT Madras. But Swaminathan and Vasant Raj are doing their PhD. Jnanadeepan is a student pursuing his MS. We also have NPTEL support staff, Mr. Karthik, who has been helping us right through in this effort. So Swaminathan will lead the interaction and will be anchoring today's discussions. So over to Swaminathan.
Thank you, Professor. And I welcome you all once again for this first live session for the course Introduction to Operations Research. Today we have Professor Srinivasan with us, who is going to directly answer all your doubts, which you have posted in the questionnaire that was sent by the NPTEL team. So the session we have planned it in the following way. First, Professor Srinivasan will start discussing the questions posted by you students on the questionnaire. Second, we TAs have made a surprising session. So what we have done is we have gone through the frequently asked questions on the discussion forum. We have collected some of the repeated questions, and we are going to take it up with Professor Srinivasan, and he is going to throw some light on those questions. Third, we are also going to look at the questions that are coming on the chat. Professor Srinivasan will be again answering those questions. So now I'm going to start this session by asking the questions posted by you students on the questionnaire sent by the NPTEL team. So before starting, I was very happy to see these comments, and I want to share this with Professor Srinivasan. Sir, most of the students have expressed their happiness with respect to the content of the course, the clarity on the lectures, and also they have mentioned that the forum has been very active and all their doubts are cleared. So these are the things that students have commented about the course. With that note, let me ask you the first question.
Yeah, go ahead. I'm very happy to hear these positive comments. This course has always attracted some good students, and the students have felt quite happy with this course. I think all the credit for managing the discussions go to the TAs. So good, happy feeling to get this kind of a positive feedback. Okay, so we can go to the first question.
Okay, sir. Could you please explain unbounded solution, infeasible solution, and slackness theorem in simple terms?
Okay, since there is a lot of emphasis on simple terms, let me try to answer them. First, the easiest thing to answer is infeasible. So infeasible means not feasible. Not feasible simply means there is no solution to the given problem. So when we say that a given linear programming problem is infeasible, then there is no solution to the problem. When we say that a given problem is unbounded, the given problem is assuming a linear programming problem. When we say that the problem is unbounded, if it is a maximization, then an unbounded linear programming problem means that the value of the objective function can go on increasing. If you go back to the relevant or corresponding examples in the course, you would realize that if the LP is unbounded, I would have explained it using a small two-variable problem. And you would see that the feasible region is not bounded at all. It will be open. And the direction of the objective function increase would be moving in the direction where it is not closed, which means you can keep increasing the values of one or more of the variables, and the objective function keeps increasing. It goes on, and there is no end, and the value is infinity. It also leads to a couple of things. Directly, this question leads to an important theorem which says that every linear programming problem is either feasible or infeasible or unbounded. Only three things can happen. When you say feasible, in this case, you mean feasible leading to an optimum solution. This optimum solution can be a unique solution or alternate optima. So there are only three things. You can get an optimum solution. The problem can be unbounded. The problem can be infeasible. Another way of understanding this part is through somewhere towards the end of the course, I would have explained how to solve problems using the Excel solver. And when you look at those videos, you would also observe that the way the Excel solver terminates exactly captures what we are trying to talk. If the problem has a feasible solution, the Excel solver will say, solver found a feasible solution, all constraints and optimality conditions satisfied. If the problem is infeasible, the solver will put out a message saying, not able to find a feasible solution. And if the problem is unbounded, it will say, cell values do not converge. There is also a very indirect way to understand these three things. I have not come to complementary slackness. I'm still staying with the question on unboundedness and infeasibility. There's a very indirect way of understanding this. I'm sure all of us would have learned how to solve equations when we were in high school. If you actually go back in time, assuming that all of us are sufficiently older, we would realize that we learned three things about solving equations. We learned three things where the given equations has a unique solution. The given equation has infinite solutions, and the given equations have no solution. If you try to map these three, that's why I said indirectly, to try to map these three into linear programming. After all, linear programming is also about solving equations. There are only three cases. Has a solution, does not have a solution. And the only thing is that has infinite solutions becomes unbounded. So that is one way to understand these. Coming back to complementary slackness, and that's a very important theorem in linear programming. It connects the primal and the dual. And the theorem simply says x into v plus y into u equal to 0, where x and y are the optimum solution to primal and dual, and u and v are the primal and dual slacks. But if you see the equation, it is x into v. X is the number of variables in the primal. V is the slack variables of the dual. And the number of variables in the primal is equal to number of constraints in the dual. And the number of constraints in the dual is equal to number of slack variables in the dual. And therefore, x and v are of the same order. Y and u are also of the same order. Very briefly, understanding the complementary slackness is, if a variable is in the solution in the primal, then the corresponding constraint is fully utilized, which means the slack is 0. That's the simplest way to understand the theorem. And the economic interpretation also would tell us that since the slack is 0 and the equation is fully utilized, the shadow price corresponding to that resource will also be equal to 0, which comes from the other way. I'm sorry. Just let me correct myself. So if a variable is basic, then the corresponding slack is 0, which means the dual constraint or dual resource is fully utilized, and therefore it has a shadow price. So the other way to understand this, if a primal constraint is not fully utilized, which means the primal slack has a value, then the theorem says the dual variable is 0, which means the shadow price is 0. So I've more or less repeated what I have told in the course, and hopefully it has been communicated in simpler terms. If the person who asked this question still has a comment, please post it in chat so that the TS will read it to me and I'll try to respond for them. Okay, we can go to the next question, Swami.
Thank you, sir. The next question is, explain duality theorem.
Again, I have to give a very long answer. I have to almost give a half a lecture for this, because a question like explain duality theorem is like telling explain linear programming. So what I've tried to do over 40 short videos, I have to explain again. As I pointed out in the course, and as you know by now, every linear programming problem has two phases to it. One is called the primal, the other is called the dual. So what does the duality theorem tell you? The duality theorem, I have explained it in a certain order, in a certain way. Different books do it differently. The duality theorem essentially tells you that if the primal and dual have optimal solutions, then the objective function value of these optimal solutions are equal. It's best explained using a standard product mix problem, which is what I have tried to do. And I'm not sure if I have actually explained it that way. There's a very interesting way to explain duality. I'm not sure if I actually have a screen in which I can show something to you. But let me check that. I'm not sure if I can share a screen or... Yes, I think there is something called present now. Let me just ask Karthik. Karthik, can I put up a... I think I can. Just let's pause for a minute. Let me try and pick up a slide and try to explain this for you. Just give me a second. I'll minimize and then open the relevant slide, and then I'll explain duality to you. Just a minute. Yeah, just a second. Let me quickly come back to this and try to, so that if I have a slide, I think I'll be able to explain it slightly better. Okay, just a second. I'm still picking up the right kind of a slide. So just give me a second. Yeah. I'm still, just give me a second. I'm still trying to pick up. Okay. Yes, just a second. I'm there. Yeah, I'm sorry. I've just taken a little bit of a time to do this. Yes, so let me see if I can share screen for you. Yes. Right, I think you should be able to see the screen. Swami, are you able to see the screen?
No, sir.
Okay. Really? Okay, sure. I'll try to share it again now. Yes, it's coming. No, I think I'm missing something. No? Illa. சரி பண்ணிட்டு இது ஓப்பன் இருக்கும்போது எப்படி நான் இங்க வருவேன் திருப்பி? ம் சரி ஓப்பன் பண்ணிருக்கேன், இங்க வந்துட்டேன். அதுதான் போட்டேன் இப்போ வரல. சரி, anyway, it's okay. Let me I'm not sure. I thought it'll be good if I do that. So I'm just checking if should I'm unable to close it also. Right now I'm sharing the entire screen. Please, my computer says I'm sharing the screen. So okay, but you're not able to see that, right? You're not able to see this. You're
No,
not
sir.
able to see a PowerPoint slide.
No, sir.
Now?
No, sir.
No.
No, sir. We
Okay.
are not.
Okay. I think let me do this. Let me see what I should do next. So just trying to. Yeah, for some reason it says share. Just hold on. Yes, can't share your screen. Dismiss. Now can you see the screen?
Sorry, sir. Unfortunately, no.
No. Okay. It says stop sharing. Stopping share. Let me go back and do present now. Share a window. I'll say share an entire screen. Okay, share. Oh, choose what you would like to share. Share. Is this fine?
Yes, sir. Yes, sir.
Okay. So now you should be able to see a linear programming problem. I must have used the same problem in the course as well. I think so. Maybe I would have used something else, but it doesn't matter. Let me just explain something with this example. So the solution to the primal, because somebody said explain the dual. So solution to the primal is x1 equal to 3, x2 x1 equal to 2, x2 equal to 3 with objective function equal to 27. So x1 equal to 2, x2 equal to 3, with z equal to 27. We type the subscripts correctly. x1 equal to 2, x2 equal to 3. So you get 6 into 2, 12 plus 5 into 3, 15 gives you 27. The solution to the dual, assuming that you can write the dual. So y1 equal to 3, y2 equal to 1, with w equal to 27. So that will give you 5 into 3, 15, plus 1 into 12 will give you the same 27. So let me try and explain using this. Now what we try to do is take this as a product mix problem. Take this as two resources that you are using. Let's say you're making tables and chairs, an example that I often give. So let's assume that let's assume that this resource is called wood, and let's say this resource is called metal. Now what is the dual trying to tell you? The dual is trying to tell you that there are two resources. There are 5 units of wood that's available with you. There are 12 units of metal available with you. And using them, you make tables and chairs. So let this x1 represent tables. So I'll say x1 represent tables. And let x2 represent chairs. A standard problem. So if you have, assuming that you need only wood and metal to make tables and chairs, assume these are the only two resources required, and you have 5 units of wood and 12 units of metal, you can make tables and chairs. You sell a table for 6 rupees and you sell a chair for 5 rupees, slightly unreasonable, but nevertheless those kind of numbers. So the primal tells you that you make 2 tables and 3 chairs and sell them and realize 27 rupees. Now what is a dual telling you? The dual is trying to tell you what is the worth of wood and what is the worth of metal at the optimum. At the optimum. When you make 2 tables and 3 chairs and sell them for 27, what is the worth or price of wood and what is the worth or price of metal? That's the dual problem. Now if you solve the dual, the worth of wood is 3 and the worth of metal is 1. And that gives you something very interesting to look at. I have 5 units of wood with me. Each is worth 3, 15. I have 12 units of metal with me. Each is worth 12. Each is worth 1. So 12. So 27, you can see me highlighting it. 27 is actually the worth of the resources that I have. Now what does the primal tell you? Make tables, make 2 tables, sell them for 2 into 6, 12. Make 3 chairs, sell them for 3 into 5, 15. And the total money is 27. So the worth, which is 27 rupees, is now converted or transformed into products which are sold and worth 27. So primal and dual essentially try to equate what is the marginal worth. I have not used the word marginal earlier. What is the marginal worth? What is the extra that you're willing to pay to buy an extra unit of wood or metal at the optimum? So what is the marginal worth of these two? And how we take these resources, make them into products such that the worth of the resource is equal to the worth of the product. Let me explain this a little bit more. Hopefully you can see me. So you can imagine that I am the carpenter who is making these tables and chairs. And you can imagine that to my left, I have a bag which has wood. And to my right, I have a bag which has metal. Now go back and see what the primal is telling you. The primal is telling you make 2 tables and 3 chairs. So to make 2 tables and 3 chairs, I need 5 units of wood I have. To make 2 tables and 3 chairs, I need 12 units of metal. So what do? Remember, the bag on my left is wood and the bag on my right is the metal. So what I'm trying to do is I take 1 unit from the wood bag. I take 3 units from the metal bag. The 1 is here, 3 is here. Let's say I kind of mix it up and then I get a table. So what is the worth of the things that I have used? I've used 1 unit of wood, which is worth 3. I've used 3 units of metal, each is worth 1. So I've taken things that are worth 6. I've made them into a table, which is now worth 6, which is what you find here. I make 2 such tables. Again, I take 1 from the wood bag, I take 2 from the metal bag, and I mix them up and I get a chair. Therefore, what I've taken things worth, wood is worth 3, metal is worth 1. So I've taken 5 worth of resources, made it into a chair, and you can see the chair's worth is 5, which is the selling price. So primal and dual are related that way, resource by resource, connecting the worth of the resource to the profit associated with the product, which is actually the worth of the product. So this, according to me, is a very good explanation of trying to understand the primal and the dual. There are several theorems which also tell you, but this is, to me, the best way to understand the primal and the dual. Right. Any next questions for me? I'm sorry I've taken a lot of time to explain this, but yes. Okay, let me minimize and let me see if there's a way to stop sharing and come back because yes, I can stop sharing and I'll come back. Right. Now please go to the next question.
Thank you for that detailed explanation, Professor. In fact, you covered much more questions that people were asked with regard to implications of primal, dual, and so on. Thank you for that. And the next question is, how to get a proper job opportunity in the OR field?
Okay, I'll try to answer this question. I know that this session is going live. So I'm only trying to give you a point of view. And this question is in some sense not a straight academic question for me to give an answer and say, this is the answer. This is more a question which has, of course, connected with academics and studies, because at the end of the day, you study and you want to pick up a job. So how do I pick up a job? First is you need a lot of expertise in the field. A course, a MOOCs course, a certification course, and a course like this gives you an introduction to a subject. It's only a beginning, and it's actually a very small beginning to move towards a career in this field. This is the first course that you would do. Depending on, of course, your age and your other qualifications and where you're working, you have to find out whether you can specialize further by doing a course that leads you to a degree, or trying to do a graduate course, which formally gives you an expertise and a qualification to say that you are quite familiar with this field. So ideally, an MTech, if you're an undergrad student now, an MTech in industrial management, or an MBA where you specialize a little more in operations research. There are institutions which are an MTech in industrial engineering where you read these subjects. And then you acquire a certain level of competence and expertise. And then you can pick up a job depending on how good you become in almost any field. I mean, today a lot of manufacturing, service industries that use data analytics, they all at some point require people with good knowledge of operations research, in addition to statistics, of course. So these two fields go hand in hand, and through formal education, I sincerely believe that while a certification course is very important, it is only a beginning to a very long journey of gaining and gathering expertise in this subject. And then you get your openings through multiple ways. Right. Okay.
Thank you, sir. Students want you to comment little bit on big M minimization and maximization, transportation problem, northwest corner rule, and so on, sir.
Yeah, I'm not sure if I'm going to tell anything new because of multiple reasons. One of which is I've told everything that needs to be told in the video, except that they can hear me speak live, as the case may be.
Right.
So I'll take each one of them one by one, but I'll do it slightly briefly. So big M is used particularly in the days, when we learned solving simplex by hand and all that. Big M was used. Big M was used particularly when we did not have when we had a greater than or equal to constraint, which doesn't give straight away a basic variable. So an artificial variable has to be used. And then you don't want that artificial variable to come into the solution. And therefore you give a large value of big M or a minimization, which becomes a very small value minus big M or a maximization. So big M is only a way to conveniently offset a difficulty and try to solve. That's why at some point in any OR course, once you learn duality and then you learn dual simplex, you don't want to go back to the big M method. So once you learn dual simplex, you would only do either what I am called as a simplex iteration or a dual simplex iteration, where you either first decide an entering variable and then the leaving variable, or you decide the leaving variable and then the entering variable. So big M is more for convenience and particularly early stages of learning. Afterwards, once you understand the matrix method and the idea that the basis is important, you don't have to really worry about the artificial variable and all that. So you replace the big M part by the dual simplex. That's the answer for the first question. What else? You said northwest corner?
Yes, sir.
Okay. Now, see, when you look at, again, today, the subject is about 70 years old. So you look at transportation problem. Most of these, if you see a book in the subject, or if you attend a class, the instructor is going to take some time and effort to tell you how to solve these by hand. If you either study this as a course leading to a certificate or leading to a degree, you write an exam, you write your exam. Maybe if you're doing engineering, you write your engineering exam. And then there's a subject called operations research. And there in the exam, you're going to solve problems by hand. So when most of these theories were developed and when most of these books were written, the primary emphasis was to solve these problems by hand. Today, if you see, we also know that beyond a very small toy problem that is often done in courses, it takes a lot of time to solve problems by hand. And today, with the availability of solvers and open source solvers, it's quite easy to try and solve a problem using a computer rather than try and solve it by hand. That's why in this course, towards the end, I've spent a session explaining to you how you solve it using a computer. So all these northwest corner Vogel's approximation, least cost method are all starting solutions, which essentially try to give you a good enough, a reasonably good starting solution, so that the optimum happens from that starting solution to the optimum. The number of iterations that you go through is small. If you compare transportation problem, which is also a linear programming problem, and you compare simplex solution to it versus a Vogel's followed by a MODI solution to it, and particularly when you do it by hand, the Vogel's followed by MODI will be faster by hand, because simplex normally doesn't care to start with a very good solution. Simplex normally cares to start with a solution which is basic feasible and may not be very close to optimal. These, particularly the transportation problem, is structured in such a way that it is possible to get a good. It's possible to get a good. Okay, it's structured in such a way that it's possible to get a good solution, a good starting solution. So if you're able to start with a good starting solution, these methods help you in getting a good starting solution, so that the number of iterations that you have to do is reduced. So that's the purpose of studying these methods. If you want to solve a really good transportation problem in practice, you'll have a large number of variables. You're not going to do it by hand. You may even choose, if you have a solver with you, you may simply choose a LP version and solve it. But there is always this nice little thing of, given a problem, how well and how fast I can solve it. This is something which every individual prides about. I can solve it faster than you. I can solve it better than somebody. So these methods were developed over a period of time to show that you can solve the same problem faster and faster, depending on how you start and what kind of an effort you put. Okay, I think that's my answer to that.
Hello.
Swami? Yeah,
Yes.
you can go to the next one.
So now we will address some of the questions on the chat. And Mr. Tiru Aruran has asked, can you please specify suitable software to solve sequencing, networking, game theory problems? Can it be solved by an open source solver?
Okay. Depends on what kind of a problem you have. I'm again trying to answer this to the best of my knowledge, and I'm not going to claim that I have the best knowledge to answer this. If you look at least the three examples that were given: sequencing, network, and game theory. If you look at all these three examples of problems given, if you ask me, is there a single solver where I can solve any OR problem? My answer is not to my knowledge. If you ask me, are there solvers even open source where I can solve linear programming, integer programming? Yes. So out of the examples given by you, a sequencing problem is an integer programming problem. A network problem, depending on what it is, could either be a linear programming or an integer program. Therefore, an IP solver and a LP solver can solve it, provided you are able to write linear programming and integer programming formulations of these problems with you for the problem that you are solving, and then you put it in as a LP and solve. If you are looking at, for example, you open a solver and then you find in one place, say, sequencing, and then you click, and then it says enter the numbers, then I don't think it works that way, because there are so many sequencing problems. So you have to find out which sequencing and scheduling problem that you are looking at, and therefore you may not be able to find an all-in-one, time. Game theoretic solutions, maybe if you have the smallest or the first version like a 2% zero sum, maybe you could still have somebody solving it, just asking you to type data and do it. Otherwise, depending on the application, you have to derive your results and solve. So a quick answer is you should know within the category of what you had spoken, what your problem is, and then you should be able to formulate it. And then you can solve them as LPs and IPs if you end up getting such formulations. Which ties up to my answer to an earlier question that this course is a beginning and only familiarizes you with very few things. So if the same gentleman asks me, will I get that ability by doing this course? My answer is very difficult. You may have to spend a lot more time. You may have to do more courses. You may have to, study further. That's why I kept on saying it's a beginning. There is another course of mine, which is a web course, which you may not find. It's an NPTEL course, a web course, where I've given some formulations for certain types of network problems, certain types of sequencing and scheduling. I've not done much in the game theory space, but I've done that. Therefore, those kind of things, when you read those topics, you read some books, and then you will understand how people have formulated their problems as OR problems, which means linear programming, integer programming, depending on whatever the problem finally becomes. And then you learn to solve the problem using these techniques. Yeah, yes, one.
Thank you, sir. The next question is from Anne. She asks, can we say that the solution to the linear programming problem is feasible or infeasible or unbounded without solving it using graphical method?
It depends, first of all, on the size of the problem. Generally, if you have a good eye for detail, if it's a very small problem, if it's a 2 by 2 or whatever, then you can look at the problem. You have to look at the numbers, and after a lot of familiarity, somebody can just say yes, it is. Unboundedness, in some ways you can check. For example, if you have a small problem, all constraints are less than equal to, but one particular variable consistently has a negative coefficient in all the constraints and has a positive coefficient. So like this you can do, but is it necessary to acquire that skill? Maybe not at the initial stage. With a lot of experience and familiarity, you may acquire it to be able to say, look at the problem and say, oh, this is unbounded, before you even try a graph or before you try a simplex to get that. But should you acquire that skill? Not easy to get it. It will take some time, but I would say maybe not. It's good to learn to solve and then try to understand. But what is important is when you solve the problem, either using the solver or by hand, if you get unboundedness or infeasibility, it is always good to go back one more time, revisit, and check that you haven't made a mistake. That's very important. That ability we should have. I think at some point I might even have mentioned it in the course that if you are solving a real life problem and then you get infeasible or unbounded, and I must have mentioned you have to do a couple of things. If let's say you go to a company and you're doing some internship, and then you formulate this problem and you put it into a solver, and then it says infeasible. Then obviously somebody is doing something, so it can't be infeasible. So if you get infeasibility, you need to go back and check whether by mistake, while typing the data or by entering, you have typed a less than equal to instead of a greater than equal to, or vice versa. That check you have to do. Similarly, when a practical problem, when model gives you unbounded, you have to check whether by mistake you put a negative coefficient instead of a positive coefficient. So these are little things that you have to take care of. Next question.
Thank you, sir. Next question is from Pawan. Pawan wants to know how to solve the slow and fast laundry problem. And he also wants to know when should we multiply -1 and when should we not multiply by -1 in the linear programming problem.
I can't understand the second question. Where is this -1 coming? -1 is coming when, see, -1 is also a trick in the sense, if you take a linear programming problem, it's either a maximization objective or a minimization objective. So just to standardize it, the way I do it, I always solve a maximization problem. I don't solve a minimization problem. There are other books, other authors, other teachers, other professors who might solve a minimization problem and not solve a maximization. If you look at it very carefully, there are, I think I must have mentioned it in the course as well. So you have maximization, minimization. You have Cj minus Zj, Zj minus Cj. So you have 4 things. Maximization, positive Cj minus Zj comes in. Minimization, negative Cj minus Zj comes in. Or positive Zj minus Cj. So all these multiplications you can do, which essentially means you have to understand maximization, minimization, Cj minus Zj, Zj minus Cj. You have to understand 4 things. Four combinations you have to understand, 2 of each. Instead of trying to memorize, and that too if you do Cj minus Zj or Zj minus Cj, it becomes 8. So instead of trying to memorize that and do it, we say, no, don't do anything like that. Just always solve a maximization problem by multiplying your objective function with a -1 if you have to solve minimization. That's where I think the -1 comes. So we consistently use only one rule that we remember always. Maximization and Cj minus Zj positive enters. So what if I get a minimization? Multiply with a -1. So that's the answer to that question. How do you solve a fast laundry and a slow laundry? Laundry problem is only an example to understand the idea of linear programming. How to solve? You can go to the solver and just solve LP. I've explained it in the course, how to solve LPs. I might have even explained the same thing for you, the same problem I would have done for you. So depending on the fast and slow, you will have different types of constraints. And once you get your constraints ready and right, you can solve it using the solver. At some point, you can also model it as a transportation problem. I think it can be modeled as a transportation problem, and I have done that in 1 or 2 places, maybe not in this course. I've also been discussing it with some colleagues about it. So, but it's generally an LP. Yeah.
Thank you, sir. So we have covered questions from the discussion forum. We have covered questions from the chat. We have also covered questions from the questionnaire. I will see if there are a few more questions on the chat, and we can conclude, sir.
Sure.
Sir, one more question. Is non-negativity a constraint? Why it can't be negative always?
Okay. So if you see the linear programming formulations, I think the same example that I have here. Let me see if I can present it again. Let me just do that and tell me if you can. Just check if you can see this. Can you see this?
Yes, sir.
Very good. So let's look at this problem. So this is a simple linear programming problem. So if I ask you how many constraints are there, the answer is 2. So x1, x2 greater than or equal to 0 is not explicitly treated as a constraint. The answer to the question how many constraints are there, the answer is 2. Why do you have a non-negativity in linear programming? You have non-negativity in the linear programming because of many reasons you have non-negativity. One of which we often tell is linear programming is about making things. I make some tables and chairs, so I don't want to make a negative number of tables and chairs. particularly at some point, if I have a problem like this, if I have a minus here, let's say, and then if x2 becomes negative, then the objective function increases. So I don't want that. So with that in mind, you don't want negative values for your decision variables. And once you are clear about the fact that you don't want negative values for your decision variables, you now try to connect it with simplex. Now the simplex algorithm, particularly the leaving variable, is largely and very clearly tied to this x1, x2 greater than or equal to 0. It's tied to that. The way we choose the leaving variable, we make sure that the feasibility is maintained, which means x1, x2 is greater than or equal to 0. Therefore, we start by saying your variables are non-negative. But luckily for me, I don't have to write them explicitly as constraints. So it doesn't hurt me. I don't have to write it as a constraint. There's still only two constraints. I just use this intelligently so that I maintain feasibility and my computational effort doesn't increase too much. Therefore, I follow this little trick to make sure that the standard problem is a non-negative LP. And then if there is a need, if one of them becomes a negative variable, then I multiply and convert it to non-negative and tweak the problem. If one variable is unrestricted, I write it as a difference of two variables and tweak a little bit so that the standard problem that I solve and the algorithm that I use to solve this problem does not change. And depending on the exceptions, the problem is sufficiently tweaked to meet the requirements of the algorithm. I think that's my answer right now to that question. Hopefully, the answer makes sense.
Thank you, sir.
Yes, yeah, I'll stop sharing again so that I can see screen. Yeah. Right. Okay.
Thank you, sir. We have covered almost all the questions. And right now, I can see 13 people are watching this session live.
Okay.
I think we've almost done this session for 56 minutes.
Yes.
If there are no more questions, I think we can end, sir.
Okay, you can ask them one last time, and then we can close the meeting.
Students, if you have any questions, please post it on the chat. Professor Srinivasan will answer that.
Okay, I think we'll sum it up, and then I'll just sum it up in a couple of minutes. So first of all, let me thank all of you who have come to this live session and participated. Let me also thank all the students who have registered for this course. Again, let me thank the TAs for this course, Swami, Vasantraj and Jnanadeepan, and Karthik, as always been, so for making this happen. As I mentioned today, it's very important that you have to understand this course as some kind of a door that takes you into a field. So which means you just enter the field by passing through a door. And that's what a training course does, or a certification course does. It doesn't give us an expertise immediately. It's still a long journey. I wish some of you, all of you, go through this journey. You have to learn a lot, you have to read a lot, you have to add more things to your learning by either doing advanced courses or by trying to join a degree program in a field where this course is useful, and then you get trained for a career in this field. Let me thank again this course, NPTEL, has helped me considerably. It's given me a lot of opportunity to interact with a lot of students through these MOOC courses, through the NPTEL videos, at times through personal emails. most of which I try to answer, and so on. It's given me a certain recognition, a certain visibility, and a certain both. It's given some expectation from my side as well as a sense of satisfaction for being able to be part of this huge learning initiative of the NPTEL, supported primarily and funded primarily by the government, and to be able to reach out to a large number of students who are interested is in itself a very, very nice thing. So I thank all of you for enabling this, and I also have learned quite a bit. With every session you learn a few things, and hopefully this session is beneficial to you. So those are my concluding remarks, and if Swami and the other TAs are fine, we can close with this. Swami?
Yes, sir.
Okay, so I think we can close with this. Karthik, we can. So you may end the session. Thank you very much. Looking forward, maybe there's another occasion where I can meet you as well. Thank you. Yeah, thanks. You can hopefully see them. Swami, I think let them again see all of you one more time. So yeah, they're able to see Swaminathan, Dhanadeepan and Vasant. Very good. So thank you very much. Thanks all the students who are present here. Have a good day. Thanks. So let me take leave. Thank you. Thank you.